The very last section of Chapter 5 on nuclear chemistry discusses nuclear fission and nuclear fusion. And before we go any further, let's just state the obvious. These two words are very similar in pronunciation and easy to stumble over. I'm going to do my very best not to, but I just want to acknowledge in advance it's tricky, and I'm going to do my best, and you're going to do your best as you discuss these topics with your classmates and try to get a handle on these concepts. So nuclear fission and nuclear fusion, this information is found in section 5.6 of your textbook. Let's take a look at nuclear fission first. Nuclear fission is the splitting of a large radioisotope into smaller atoms with the production of a tremendous amount of energy per gram to kilogram of radioisotope that reacts. Note that fission can be initiated by neutron bombardment of uranium-238. So not every radioisotope is capable of undergoing a fission reaction, a splitting reaction. Uranium-238 is a fissionable isotope. It can split into smaller nuclei, but in order to start that splitting process, it needs to be bombarded by a neutron. There's several different ways that uranium-238 can split in a fission reaction, and up here on the board is one of the ways that uranium-238 can split. So notice it has to be bombarded by a neutron. When the neutron collides with the nucleus of a uranium-238 atom, it can initiate the fission, the splitting of uranium-238, possibly into these two isotopes, krypton-91 and barium-142. In addition to a krypton-91 isotope and a barium-142 isotope, you also produce 3 more neutrons in the fission, in the splitting process. And that is going to be a very significant piece of information. But before we get to that, I want to mention that as stated in the fission definition, this process is exothermic. It releases energy. The reason that it releases energy, and a tremendous amount of energy if you have a significant amount of uranium-238 reacting, the reason it produces so much energy is that you actually lose mass, a little bit of mass in this process. The total mass of the products is slightly less than the mass of the reactants. And what happens when that mass is lost? According to Einstein's famous equation, E equals mc squared, where E stands for energy, m stands for mass, and c stands for the speed of light, which is squared in this equation. A small amount of mass, when multiplied by the speed of light squared, can produce a tremendous, or release a tremendous amount of energy. So a strongly exothermic reaction, energy released tremendously greater than what we see in standard chemical changes. This is a nuclear change, way more energy released. Now let's get back to this discussion of these 3 neutrons that are produced. Remember, it takes 1 neutron to initiate the fission, but you produce more neutrons than is needed to initiate. Because of that, because you produce more neutrons in the process than is required to start it, it creates the potential for a self-sustaining nuclear chain reaction. If you have your textbooks open with you, it would be really helpful to take a look at figure 5.7. This is found on page 167 of your textbook, and it gives a much better drawing than I'm able to do here with limited board space. But if you don't have the textbook present or don't have it at all, let's see if we can't give you a little idea. Here's a uranium-238 isotope. Here's the incoming neutron that's going to collide with it. The red squiggle means fission happens. You produce these two daughter isotopes, which I haven't drawn in because it's too crowded. So you produce two smaller isotopes, but you also produce 3 new neutrons in the fission. And here are those 3 neutrons. If there are nearby uranium-238 atoms close by, these 3 neutrons can then initiate fission in 3 more uranium-238 nuclei. Then they split, and now you have 9 neutrons released, which, if there are nearby uranium-238 isotopes present, causes them to undergo fission and split. So you have an ever-increasing number of neutrons produced in this cascading, increasing process, which creates a self-sustaining nuclear chain reaction. Now notice what's critical is that you have to have uranium-238 present in sufficient amount to capture the neutrons that are produced. So you have to have enough uranium-238 present, purified in one place, so that these neutrons have a great probability of encountering a nearby uranium-238 isotope. So that leads us to this concept called critical mass, which is the minimum amount of fissionable radioisotope needed to be present and pure, very, very pure, for a nuclear chain reaction to occur. And part of the significant Manhattan Project that occurred in the U.S. during World War II, a critical part of the research of the Manhattan Project was to experimentally determine what the critical mass of uranium-238 would need to be in order to have a self-sustaining nuclear reaction. And then once they discovered that, to then actually be able to obtain purified uranium-238 and construct a nuclear device, an atomic bomb, that could create the reaction, but at a controlled manner, in a controlled way, when desired. Nobody wants to be walking around holding a critical mass of uranium-238, which could then just react in an undesired, untimely manner. So the Manhattan Project, top secret project conducted by the U.S. military to be able to explore what the critical mass of uranium-238 would need to be, and then develop that into an atomic bomb. Which leads us to uses of nuclear fission. One is atomic bombs that were used during World War II at the end on the cities of Hiroshima and Nagasaki. Those were nuclear fission weapons, one being a uranium atomic bomb and the other a plutonium atomic bomb. And I could pause and stop here about the profound consequences to the reality of this entire planet because of the development and use of atomic weapons. It's sobering to think that we will never be able to turn back the clock and imagine a world free of the potential devastation that is created by nuclear weapons. Now the job ahead of us is to make sure that as a species with the power to create and to control the use, that we make sure those weapons are never used again. There is another application of nuclear fission, and that is with the use of nuclear power plants, or in the use of nuclear power plants. Nuclear power plants use a controlled nuclear fission process in order to generate electricity. And there are many, many places across the planet that rely heavily on nuclear power plants to create electricity. There is a significant issue with the use of nuclear power plants. There are several issues, but one that I want to point out that we still struggle with is where to dispose of the radioactive waste generated by nuclear power plants. We don't, in the U.S., have a really good solution to that problem yet. Both Krypton-91 and Barium-142, both of these are radioactive waste products that are dangerous and hazardous, and we still haven't figured out a good solution to where to dispose of the radioactive waste generated by nuclear power plants. Let's transition now to the second process that I'd like to discuss, which is nuclear fusion. Not fission, but fusion. Nuclear fusion is the joining together of two small nuclei to form a larger nucleus with a release of tremendous amount of energy per gram to kilogram of reactant. Even more energy is released per gram in a fusion process than in a fission process. So even more energy is produced, extremely exothermic. And that is ultimately linked to the fact that the products of a fusion reaction have less mass than the reactants. So as you move forward, you lose mass, and a small amount of mass multiplied by the speed of light squared produces a tremendous amount of energy. So I'd like to point out an example of a nuclear fusion reaction that occurs in our sun as well as in other stars. So notice this fusion reaction involves two different isotopes of hydrogen. Tritium and deuterium can fuse together. These small nuclei join together to produce a single larger nuclei, the helium nuclei. Notice that a neutron is also produced in the fusion reaction along with energy. Even more energy per gram than a fission reaction. So notice one important distinction is that the products of a nuclear fusion reaction are not radioactive. Helium is a very stable, unreactive nuclei. Neutrons are regularly produced and released and not harmful, particularly unless they happen to collide with a critical mass of uranium-238. So they escape into space and by and large do not create a problem unless they can initiate a nuclear fission reaction. So the products of nuclear fusion are not radioactive, unlike fission products. So we would love to generate electricity by using a nuclear fusion reaction, no radioactive waste, but unfortunately, nuclear fusion requires extremely high initiating temperatures to occur. Temperatures like the internal temperature of the sun, which is a huge nuclear fusion reaction. We're talking about millions of degrees Celsius temperature needed to initiate fusion. And why is that? Because these two nuclei have to collide together and join. Well, what do we know about the charges on nuclei? They are positively charged. So you get two positively charged nuclei in close contact, they repel. they push away. The only way to overcome that electrostatic repulsion is to have them moving incredibly fast, generated by these very extreme high temperatures, as in the center of the sun. When they're moving that fast, because they're that hot, it overcomes the repulsion forces and enables the nuclei to join together, to fuse together, to form a larger nucleus. So here on planet Earth, in order to have a nuclear fusion reaction take place, we have been able to generate it in a sustained manner, but it actually cost more energy to initiate the fusion than was produced as a product. So obviously not economically sustainable right now at this time for us to use nuclear fusion as a way of generating electricity. But I know that research continues to try to lower that temperature and make nuclear fusion more feasible as a way of generating electricity. So, what are the current uses of nuclear fusion? Well, in the universe, nuclear fusion reactions generate energy released by sun and stars. So ultimately, planet Earth, which relies on the energy generated by the sun, is powered by that nuclear fusion reaction happening in the sun. Here on Earth, the only use for nuclear fusion that we have perfected and tested is, unfortunately, another type of weapon, an even more dangerous weapon than an atomic bomb. It's called thermonuclear weapons or hydrogen bombs, which rely on a fusion reaction like this to generate even more power in an explosion than an atomic bomb. So we have developed hydrogen bombs. We're not the only country to have done so, and it behooves all of us as citizens of the planet to make sure thermonuclear weapons are never used.